To further understand the DLVO theory, let's watch this quick 5-minute lecture on this theory.
Hello and welcome to another 5-minute video for Level 3. In this session we're going to be talking about DLVO theory. So what is DLVO theory? Where's the DLVO come from? These are the initials of the people who developed this theory. Djangoin, Landau, VOA and Overbeek. Actually, this pair developed the theory, and simultaneously this pair also developed exactly the same theory, so we put them all together and it become known as the DLVO theory. It's all about summing together at molecular level molecular forces of attraction and molecular forces of repulsion and seeing what the net effect is. Quite simple really. So it combines van der Waals forces of attraction and the forces of repulsion that we defined in the electrical double layer. And this theory explains coagulation of colloids, and it explains the stabilisation of colloids. And we can also identify what we call the primary and secondary minimum of colloidal systems. So here we have a graph, we'll just go through it slowly. These are the repulsive forces. Imagine having two magnets, North Pole to North Pole. When they're far apart, you can't feel any forces of repulsion. As the magnets get closer together, the forces of repulsion become stronger and stronger. So, going back to our video with the electrical double layer, forces of repulsion, as two particles get closer and closer together, then the repulsive forces will increase. Now imagine switching these magnets around, one of these magnets around, so we've got a north and south pole. Again, at a distance, there's no attraction because they're too far away. But as you get closer and closer, those forces of attraction will become stronger and stronger and stronger. So this blue line here represents forces of attraction. So whenever we have two colloidal particles, or two particles together in solution, they both exhibit forces of repulsion for each other and forces of attraction for each other. So what we do is we sum those two forces. At each distance we add the forces of repulsion and the forces of attraction. They cancel each other out, see what we get. And this next slide, so there are the forces of attraction that we had, forces of repulsion that we had, those are the forces of attraction that we had. And when we add these curves together, the red line represents the net curve. So what it's showing is, as two particles approach each other, the repelling forces are dominating, so they want to stay far, far apart. The closer you get, the more repelling force, the stronger the repelling force. But the strange thing is, once you get beyond this point here, the forces of attraction now become greater than the forces of repulsion, and therefore in this area the particles will be attracted to each other. So what this could mean, for example, is you could have a colloidal suspension and the colloid will be nice and stable, all the particles will be individual, nothing will ever settle. But if you did something like mix it incredibly vigorously, then by mixing up very vigorously, you will force the particles closer together than they might otherwise have ever achieved. And by going beyond this limit, by forcing them together here by mechanical action, you will then make them attract to each other, and your colloid will then become unstable and it will coagulate. If we manipulate the chemistry of the system so that we change the nature of that electrical double layer, change the size of it, then what we're going to do is to change one of these curves. So here we've got two different curves. There again are the forces of repulsion, there are the forces of attraction. Because we've changed the chemistry, as you see here, in this area here, the particles do want to be attracted to each other. so they do want to come together. So this may be, for example, getting things like MF and UF resin particles adsorbed onto the surface of fibres. But at this point here, at this particular distance away, the forces of repulsion take over, and therefore the fibre and the particles of resin do not want to be attracted to each other, they're repelled. But if you can go beyond that, then the attractive forces will take over. So this, as always, is known as the primary minimum, and that's what we have in most systems, the primary minimum. But occasionally, in some systems, you can also have this secondary minimum here. So we've identified now primary minimums and secondary minimums. And this could be manipulated by things like pH, as an example. So that's all I want to say about DLVO theory. Just a very quick summary for you. DLVO theory is all about summing attractive and repulsive forces between two particles. This helps to explain coagulation, when things can get together, and it explains colloid stabilisation, where we keep them apart, and finally sometimes in these systems you can observe secondary minimum, and I hope I've demonstrated how the secondary minimum can come about. Okay, well, thank you for listening to this video, and I hope you'll follow us on this social media.